So what's going on, guys? Let's go over this multiple choice, okay? If ax equals lambda x or some vector x, then lambda is an eigenvalue of x, of a, I mean. Well, think about it. Is this true or false? Read the definition of what an eigenvalue and what an eigenvector is. It's false, because, look, for lambda to be an eigenvalue, x has to be a non-trivial solution. Do you see non-trivial solution anywhere? Nope. A is false. Look at B. A matrix A is not invertible if and only if 0 is an eigenvalue of A. Okay, well, let's go back to this example 5. Look right here. You have A right here and you have B right here. The eigenvalues of A are this and the eigenvalues of B are that. So, sorry. The matrix is not invertible if and only if 0 is an eigenvalue of A. Well, that's true. If 0 is an eigenvalue of A, that means 0 is along the diagonal because of that theorem. Theorem 1, okay? So this is in fact true. If 0 is an eigenvalue, then it must be along the diagonal. And if you have a if one of the diagonals is a 0, the determinant becomes 0, and so therefore the inverse is undefined because you have to multiply 1 over the determinant by something. What I mean is you have to do a 1 over the determinant and then multiply d minus b minus c a to get the inverse, okay? So this is true. A number c is an eigenvalue of a if and only if the equation a minus c I x equals 0 has a non-trivial solution. That is correct. This a minus c I x equals 0 is the same thing as ax equals lambda x. These two forms are the exact same thing, okay? And so this is true. For c to be an eigenvalue, there must be a non-trivial solution of this equation form, okay? There's no other way around it. D. Find an eigenvector of A may be difficult, but checking whether a given vector is in fact an eigenvector is easy. Finding an eigenvector may be difficult, right? Because you have to do like row reduce and stuff. But checking whether a given vector is in fact an eigenvector is easy, right? Because if you have a vector and you have your matrix, you multiply them together and you see if the result is a scalar multiple of the original vector. And that's how you tell if something is if you found eigenvalues, okay? And eigenvectors. So this is true. So now we're going to go to this one, E. To find the eigenvalues of A, reduce A to echelon form. Well, this is false. This is definitely false because look. Where is it? That's not where it is. Right here, look at this example right here. We went through this. Ax equals 7x, a minus 7ix equals 0. You solve it, and then you solve this. You solve this a minus 7i. You form the augmented matrix, and you get the solution of the form x 1 1. Okay, and what the multiple choice was saying is this: to find the eigenvalues of A, reduce A to echelon form. No, you want to reduce this to reduced echelon form. So that's false. Okay, let's move on. let's go to A. If ax equals lambda x for some scalar lambda, then x is an eigenvector of A. No, that is false. X has to be a non-trivial solution. Got that? Non-trivial solution. It's false. B. If v1 and v2 are linearly independent eigenvectors, then they correspond to distinct eigenvalues. This is false. You know why? Go back to example 4. Look, here's... Wait, sorry, I need to read the question again. I almost forgot the question. Oh, yeah. Okay. Look at example 4. These two right here, they're linearly independent are these eigenvectors? Yes. These are linearly independent eigenvectors, okay? And look, they correspond to the same eigenvalue, okay? The same value too. So let's go back down to this multiple choice. If v1 and v2 are linearly independent eigenvectors and they correspond to distinct eigenvalues, no, that's false. C. A steady state vector for a stochastic matrix is actually an eigenvector. A stochastic state vector for a stochastic matrix is actually an eigenvector. Ooh, that one I'm a little unsure of actually. Let me see if the text had it. So, as another example, readers of section 4.9 will recall that if A is a stochastic matrix, then the steady state vector Q for A satisfies the equation AX equals X. That is, AQ equals 1 times Q. Okay, so, whoops. So what we just read, right, was A times P equals 1 times P. Okay, so C is true. The eigenvalues of a matrix are on its main diagonal. Is that true or false? Ah, there's a trick in here. This question did not say that the matrix was in reduced echelon form. If it's not in reduced echelon form, then this is not correct. So this question is false. The eigenvalues of a matrix are on its main diagonal if and only if it's in reduced echelon form, okay? D. An eigenspace of A is a null space of a certain matrix. This is definitely true. I explained what the eigenspace was in the last video. You should watch that, okay? I hope this was helpful. I'm going to sign off now.